Let's move on to our next talk by John Paice. John will be introducing us CORSIM, a correlated timing observation simulator. John, please share the screen.
All right, can you see that?
Yes.
Wonderful. All right, hello, thank you all for coming and thank you for giving me the chance to speak here. So yes, I am going to be introducing a program that I've written called CORSIM. This is the world premiere, which means I've not got around to telling people before. So the main motivation behind this project is a couple of problems that face every observational astronomer. I hope these are worldwide problems, or else I have grossly made a big error. But anyway, the first problem is, how can I be sure my observation will give me good data? You obviously, you sometimes have to ask, like, is the observation long enough? Is the source bright enough? Like, am I going to get good data when I ask for it with these parameters? And the second is, how do I know my data are representative of my source? How do I know that any features I see are real, that there's something in the cross-correlation function? Is that something that's just noise, or is it actually something that is real? After all, what we're doing is we're having one finite observation of what is a much larger process, so there's an inherent problem there. And for multi-wavelength astronomers, or even just multi-band astronomers, you can multiply these difficulties. You've got to make sure your count rate is definitely high enough. You've got to make sure the observation is definitely long enough to either split that up or even have both telescopes looking at the same time. So it's one of these sort of big problems, the overarching problems that face the field. And part of this motivation is what got to CORSIM. So CORSIM is a program that I've been writing with help of my supervisor, Project Gandhi and Ranjiv Misra over the past couple of years. And it's a way to simulate multi-wavelength observations using a Fourier description of your source, the properties of the telescopes involved, and a variety of noise sources. A little note, a lot of CORSIM is powered by Stingray, so absolutely go check out that wonderful Python package if you can. So what does CORSIM actually do? So what you do is you input those things that I mentioned before about the source, the Fourier description and everything, and the telescope description, and it simulates observations for you. So it simulates a multi-wavelength observation of two different bands. Here you can see the light curves in blue and red. What it then does is it then sort of works back on itself, and it starts trying to work out the cross-correlation function and the Fourier features of each of those observations. So you sort of have if this is my model and I run it through the corrupting filter of an observation, what is going to then come out the other side when I observe that, as it were? So you have here on the left, you have all the input data, the models, and on the right, what you would see on a given observation. And this is based on data from my 2019 paper from the HyperCam and NISA instruments. The full list of possible parameters are listed here. So you've got the count rate, fractional RMS of the source, and various Fourier descriptions of the source, such as power spectrum and time lags. Various observational parameters, like how long you're going to be observing, the time resolution, and various factors of the optical telescope, if you have it, and also various noise factors as well. What else can CORSIM do? Well, one of the main things you can do when you're doing this is you can start comparing different parameters. For example, what does changing the length of the observation do? Here we have three different sample observations in red, green, and blue. And you can see that by increasing the time from 200 seconds on the left to 4,000 seconds on the right, the cross-correlation function is a lot more matching the input in black, The power spectrum, the errors are going down, the coherence is becoming a lot closer to the input values, etc., etc. We can also compare the effects of count rate. You can see in 10 counts a second, we're barely getting anything. There's too much noise. 10 counts a second just isn't good enough for this particular observation that I simulated. But if you go all the way to 100 and 1,000 counts per second, you start seeing some differences there. You can simulate so much more as well. So here is a comparison with just various different ideas. So same observation with different changes. Do I want a longer observation? Do I want a lower resolution observation to reduce some of that readout noise? Or do I want a better telescope? So I can sort of put in very different parameters. I can tweak them around to try and work out what observation will be best. But so far, I've just talked about before an observation happens, but core sim can also be useful after the observation has taken place. So this is, for example, analysis that I actually used in my 2021 paper on the very famous LMXB MaxiJ 1820. And what was going on with this source is we wanted to look at this particular feature in the cross-correlation function. So this is this red line here. We saw that there was a great correlation at just negative light between the X-ray and optical bands. And we were wondering, okay, well, what is causing that in the phase lags? So we got the model of the phase lags. You can see them all in the red lines here. And then we modified them to remove a certain part that we thought was relevant. And indeed it was. And so if you go over to the green and yellow lines, we start playing around with different models. What if we take out this QPO that we saw in the source? What if we take out these negative lags but leave the QPO? And we get to sort of parse out what various features in the correlation function are dependent upon the features in the Fourier description of the source. So you can sort of look at a source afterwards, look at your data afterwards, and you can start putting in various models to work out what is most important there. Another motivation behind CoreSim was to try and look at errors in these various features. So like in Fourier observations, you get a lot of errors in the power spectrum and such. In correlation functions, if anyone's ever used correlation functions, then you'll probably know that errors are a bit of a nebulous arcane matter. And this program, by simulating a bunch of observations, we can start looking at what are the error values for each one. And here, for example, is just one sample observation that was done at various different observation lengths. And you can see how the error decreases as the observation gets longer. So, you know, it's not a new realization to know that the longer you observe, the lower your errors are going to be. But getting to actually see when your errors reach certain levels is a strength of this program. For example, if you want to say, have a power spectrum where your errors are on average only about 10% of your values, you can just simulate this sort of diagram with your observation, and you can say that for this particular one, 10% is reached at about the 50 to 100 second marks. That's how long you have to observe to get that level of error in your power spectrum. So now for the big reveal that it is not out yet. So I am still working on the paper for course, and I'm still working on the programs, just changing things here and there, but a lot of it is broadly there. I still need to do things like learn how GitHub works and put it on there. But that is all going to happen in the future. I'm very excited for this. I am actually very open, not only to questions, but also for comments right now. I want to know, what part of this sort of program would you like to see? What is interesting about this to you? What would be useful to you? Is there anything that I've missed, anything that I've not really covered yet that you'd like to see? And also, I realize that this is essentially reinventing the wheel in some regards. The simulation softwares out there are 10 a penny, and they all do fantastic work in their own little niches. So are there any that I am very similar to, and how can I therefore make this program distinct in a useful and impactful way? Teşekkürler.
Thank you so much, John. It sounds quite exciting. I can think of a couple of things. Let's see if there is any comment, question to John.
Hi, John. This is Emrah.
Hi, Emrah.
Do you take dead time effects into account? Because I didn't see that in the list. I mean, every instrument have a different dead time profile, which would affect all these simulations, I think.
Yes, I do. Currently, dead time is only tied to if you're using an optical telescope in the calculation of scintillation noise. But I do include that as a feature. I suppose what you would usually do when you use this is you would find what is the kind of general count rate on your telescope, which would be including dead time, and then put that number into the program. But if there are other ways that dead time starts affecting things, I can absolutely look into including that.
Eda, please ask your question.
Hi, John. So I was going to ask about those noise contribution while you're simulating the spectrum, because you are including the several sorts of noises, right? So would it be possible to extract by using all those options, would it be possible to extract the intrinsic noise for the source, you know, from the data if we simulate, if you put all those information into your simulation so that we can understand, you know, the contribution of the intrinsic noise?
In theory, yes. I would say that this program is probably not the best for that. So I'm just using very simple. Right now, there are only very simple methods for calculating noise and observations. So, for example, white noise, I would just be adding on a random, normally distributed number on top of the count rate, for example.
Okay, like Poisson noise.
Yeah, like Poisson noise. So any sort of trying to find the intrinsic signal beneath the signal you have, there are going to be other programs out there that will do it a lot better than Poisson does.
Okay, thank you.
Well, thank you very much for question. It's a good question. I can also show the various noise sources and how they affect here in some various slides we've got.
Thanks a lot, John. Once again, I'll be looking forward to your release of this program.
So will I.